Good evening, 6 o'clock. Let's get started. So tonight we have this multiplication. Topic of multiplication, how is it done? That's what we're supposed to discuss. Let me see if there are any questions on the discussion board. Okay, module 7. Okay, so I see there are two from Carter. One is, how does adding 1 to b in 2's complement subtraction formula gives a 2's complement of b? So basically this one is how we compute 2's complement form, okay? Or how do we generate a 2's complement form? This one is more like this. Let me share my Jamboard with you guys. Okay, so let's say I have this a bit pattern, right? A bit pattern B, and I want to transform it into negative of B. Okay, so what I do basically to do that, I basically on the bit pattern I do an inversion of B plus 1. Okay, this is how we do the 2's complement. For example, let's say I am representing let's say 5-bit 2's complement, which means the range is about minus 16 to 15, right? Is 5 bits, so 2 to the 4, which is 16, minus 16 to 15. Okay. Now that means a bit pattern like this, 0, 1, 1, 0, 0, like this bit pattern in base 2 is practically equal to your 1, 2, 4, 8, 16, 12, right? Now, what is minus 12 in this form? In this form, minus 12 is represented with 1, 0, 1, 0, 0. Okay, 1, 0, 1, 0, 0. 16, okay. Now, if you see that if you do inversion of 0, 1, 1, 0, 0 plus 1, if you do that operation, it becomes like 1, 1, 3, 1, 0, 0, 1, 1 plus 1, and you add them up. 1 plus 1 is 0. 1 plus 1 is 1, 0. Carry forward 1. It will give me 1 plus 1, 0. Carry forward 1, which is 1. Carry forward 0, then 1. Now see here your this pattern is this pattern, right? So practically we pick up this pattern, invert it, and add 1 on top of that to derive into its negative number. Now you see, like if you actually do the reverse one, which is this one is represent minus 12, and this one is represent plus 12 in 2's complement form. Now, if you do the reverse translation, you will actually end up here. Means if you do an invert of 1, 0, 1, 0, 0 plus 1, which is basically 0, 1, 0, 1, 1 plus 1, which if you sum it up, you will get 0, 1, 1, 0, 0. Okay, so that's the beauty of the 2's complement representation, that its negative and positive representation can be done, conversion can be done very easy way, and which is practically your this formula, inversion of the bit pattern plus 1. So that's why that's how it is basically done in the subtraction, where we are trying to do basically a minus b, assuming let's say a and b both are positive quantity or values. Then we can simply do a addition of minus b, then it it becomes nothing at the bit level operation. It's nothing but inversion of the bit pattern b, addition of 1. Now you see there is this addition of 1, extra addition comes up in the subtraction, and that's what it's doing in the in our subtraction circuit. Carter, is that clear now?
Yeah, that's clear. Thank you.
So just to double check,
Yes.
you have a 2's complement number. You always check the MSB to be sure if it's negative or positive?
Not really, you don't need to, right? Because it's a value, right? So that means these can be either positive or negative. These can either positive or negative. So it doesn't matter what representation it comes in. If you do this logical function, it will bound to give you the result of a subtraction between these two values, no matter what the sign of those values are.
Right.
Okay, any other questions on this part? All right, next one from Carter, simplified sequential multiplier and how the result, the finalized bit shifting. Okay, this is interesting. So let us do an example, okay, in both way. Either it's an like non-simplified, which gives you which require you to have like double number of bits in the addition circuit, addition subtraction circuit. Like for example, 32-bit multiplication, the algorithm you follow needs a 64-bit adder. Let's discuss that process, and also the other process where you need a simplified ALU. 32-bit ALU is sufficient for doing the computation for multiplication. We'll pick up 4-bit for simplified discussion, but you can extend the similar concept in the 32-bit or beyond, like any number of bits you want to think of. So let's, I think this is end of the board. So let me go back to board number 1. Okay. Now let's take an example. Let's take an example like this. Maybe 1011. Okay. And now let's take, let's assume that is multiplicand, and then let's see. Let's take another number. What? Duplicate. This is multiplier, let's say. Unsigned value. So it's basically these two are which values? 8 plus 2, 11 multiplied by 9. So I'm looking for an answer 99 there at the end of the day, right? So let's see. Oops. Okay. Now we multiply 1 with this entire multiplicand bit pattern, right? So with that, we actually get the same value in the first step, and then we multiply 0 with the bit pattern, multiplicand bit pattern, which gives us all 0. So I'm talking about the one where we are using like larger adder circuit. Like if it is a 4-bit multiplication, we need an 8-bit adder for that. Why is that? Conceptually, it is not a 4-bit result, but conceptually it is always a 8-bit, and which 8-bit is kind of silent. It's always there, but it is not apparent from paper pencil standpoint. But conceptually, these extra 4 bits are there for case of the 4-bit multiplication. So we are actually doing an 8-bit addition at this point, 8-bit addition at this point, and which gives us this one definitely, and which the result becomes this, right? If we add them, it becomes like that. So in this case, we kind of say that this is finalized. I will say why it is finalized, but this is an intermediate step after 2-bit of operation done, right? Then we need to do the similar thing for this guy. Hey, wait a minute. I probably did miss up something. So this one has to be shifted. Okay, this one has to be shifted. Paper pencil, remember, 1-step shift. It doesn't change the result though. Let's see. It's a 3-bit, extra 3-bit over here. And let me duplicate that one. And let's say 1 bit here. Okay, so basically what I'm saying, your multiplication between these two, this one and this one, result in this part of the whole system, whole scenario. And we append the default 0 on this column and 3-bit other default zeros to make everything is 8-bit, and then your summation happens. Then your summation happens at that point, partial summation. Now on the next step, what we are doing, we basically need to multiply this with the multiplicand, which will give us similar, like on the paper pencil, you'll see it will be shifted like here. We write it down under here, and let me duplicate this one. This one will be like 2 zeros. Okay, and another 2 zeros will be coming at the other end. Let me change the color. Okay. So now see, like with a partial product, we are basically start shifting around my numbers, right? Just to give an one-to-one correspondence with the paper pencil method, like what we in the paper pencil we do is this, right? We write down 1011 first step, and second step 0000, and third step one, okay, it's still 0000, and fourth step we do this 1011 and add them, right? And we assume these columns has 0 0 0 0, and on the above these columns are 0 0 0 0 0 0, something like that, right? So it becomes like your result ultimately become 1 1 0. This column is 1 plus 1 0, carry forward 1, 1 plus 1 0, carry forward 1, which is 1 and 1. So this becomes your result at the end of the day, which is, let's figure out which is what. This is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5, 2 to the power 6, right? So it becomes like 3264 plus 32 plus 2 plus 1, which is 2 plus 1, 3. This is 35. 5 plus 4, 9. 6 plus 3, 9, 99. So that's what our expectation was. This gives 99 multiplication result. But in the electronic process, in the logical steps, what is going on behind the scene is this part, right? Where we are doing the partial summation at each step. Okay, now we're done with the bit 1, bit 2, bit 3. So last bit is need to be counted for. Okay, let's write down the summation, partial summation at that point. So this becomes your is the same thing. Is the same because it's addition with the 0. Duplicate. Okay. Now we have to have these two summation done. This one with this. So that means that part will come under one more shifting. And we add extra zeros at the one end. And other end we do give another 0. So this one. Now you add them up. So addition would be, result would be like this. 1 plus 1, okay, let me, okay. 1 plus 0 is 1, and then 1 plus 0 is 1, and then 0 plus 0 is 0, then, okay, how much we did? Let me just write it down. So 1 plus 0 is 1, 1 plus 0 is 1, 0 plus 0, 0, 1 plus 1, 0, carry forward 1, 1 plus 1, 0, carry forward 1, which is 1 here, 1 here, 0, which is same as the one we did for the as a paper pencil method, right? So here you see at each point, at each partial addition, we actually need to deploy a 8-bit addition process, whereas my target multiplication is a 4-bit multiplication. Okay, so now we will try to go and optimize on that to understand how that process works. Question so far? Okay, now let's pick up the same example. 1, what was that? It was 1, 0, 1, 1 multiplicand. Our multiplier was multiplier was 0. Okay, so 1001 multiplier. So we are trying to do multiplication on that. Let me draw one more line in that process. Okay. Now we need to, okay, in this process also we start with this this bit, multiply it with this bit, this series of bit, and we get a multiplication result. Okay, duplicate here at this point. Now what we are saying is that we are just shifting this guy one position and add, let me duplicate that, add a 0 in that process. Add a 0 in that process. So it will be an artificial 0 we are inserting. So add a 0, make it a 4-bit. Now we deal with this next bit multiplication, which will have again 0, 0, 0, 0, right? Zero, 0, okay. And now we do addition on this 4-bit. So we actually want to do addition on this 4-bit because we are finalized that bit already. Okay, so addition on this 4-bit. So this 4-bit will result me this thing, right? Mm, 1, 0, 1, 0. Yep. Okay. And remember, we already have the other side. We already have another 1. So let me introduce that back, which is finalized. Okay. Let me change the color code a little bit. Let me put it in a red, and let me put it in green. Okay. Now we have that already at this point finalized. Now we shift the whole thing again. This whole thing is shifted. So that means we are shifting this one and shifting this bit pattern. And within that process, we are adding 1, 0 here. Now we do this same process with this 0, right? Next bit of the multiplier. So it will result in similar like that, all 0. Let's duplicate it. And then do our addition. So which will become Similarly, like, okay, which will become like, my partial product will now look like 0, 1, 0, yeah, 0, 0, 1, 0. Okay. And remember, we already have these two of them finalized over here, this one and that other one. So let me duplicate that, which is finalized. Okay. And at this point, now we shift this whole pattern again. So with shifting means it will go one bit this side, and finalize this, and add and 0 at the MSB side. And now we deal with the last bit MSB of the multiplier, which will give me this partial result. We add them and we get a result okay, which is 1 plus 1 0, carry forward 1, 1 plus 1 0, carry forward 1. Okay, this one, and we already have finalized result bit, which is 0, 1, 1. So together, you see, we get 1, 1, 0, 0, 0, 1, 1, which is same as 1, 1, 0, 0, 0, 1, 1. Is the same result. We obtain same result of the multiplication, but using 4-bit addition. Unlike the previous method, where we actually had this 8-bit addition there, 8-bit adder there. We needed to have that 8-bit addition. In this process, we actually can live with 4-bit addition at a point. So that is the simplified circuit. Make sense? Question?
So essentially, the thing that simplifies it is just right shifting the partial products.
Yes. Why we can live with that? Because you see, like, at this point, right? If you look at this column, it is that very first bit is added with all the zeros, right? So it is as good as we are finalized in this bit. So we don't need to even worry later about what is the addition become, right? And then if you think in terms of partial product, these two term addition, whatever the partial product gives in between here, right? And then you can, everything else is added with 0. So that means at this point, I can finalize that bit. So that's the philosophy behind, like shifting and finalizing bit at each partial step.
After you finish the multiplication, though, don't you still need to shift it by 1 bit to the right?
Exactly. I was coming to that point. Thank you, Rachel, for thank you for mentioning that. Yeah, so you see, like, this is still 7-bit, this one. This one says 7-bit. So to finalize the whole process, you need to actually shift by 1 more bit to make it 8-bit. So it is still 7-bit, like by the operation that you can see. But to complete that, we want to shift it 1 more time. Okay, so this becomes this, and so this is your complete 8-bit product, as you see, 0, 1, 1, 0, 0, 0, 1, 1. Question.
Yeah, is it fair to say that you will shift your product the same number of bits in your multiplicand and multiplier, or multiplier, I should say?
I think so. Let's look at like how many, like 1 shift, 2 shift, 3 shift, 4 shift. Yeah, four yeah, 4 bit multiplication, 4 shift is happening. In fact, let me explain a little more detail here. I think I need to tell you where from this 0 coming up. Okay, where from this 0 coming up. So see that each step, remember your sum operation, sum operation actually gives 2 results, right? Or I'd say addition operation gives 2 results. One is a sum bit and other is the carry, right? So in fact, the 0 you are seeing here is not a constant 0 that we always insert here. They are basically carry out from the addition. So what I mean is that, let's say I have like, let's concentrate on this step. Okay, so I got, let's say at that point, for some other example, I got something like this: 0 1 1 1 0 1 1 finalized bit, and under that I have 1 1 0 0. Okay, so what I do here is basically doing the addition: 1 plus 0 1 plus 0 1 plus 0 0, carry forward 1, and that will give me 0 and carry forward bit as 1, right? So now at this point, what we need to construct the 8-bit, because this is 7-bit, right? To construct the 8-bit, we need to account for this carry out bit as well. Do you see my point there? So these zeros are not just fixed 0 that we introduce. It's basically carry out from the previous step, previous addition. Maybe we can actually do one example like that, where we actually do the carry out of the previous. So let me again pick a number, right? Let's say 1011. Let's have a bigger number, 1101. Okay, which is what? Which is 1 2 4 8 8 10 11 multiplied by what? 12 13. Is it 11 multiplied by 13?
Yeah.
So this one is 11 multiplied by 13, which is 341 143, right? And 143 means we are kind of expecting 64 128. Okay, 2 to the power 7, 128 plus 64, 128 plus 64, which is anyway, let me use the calculator. Just hold on. Let me use my calculator to look at the bit pattern quickly. Programmers, we're talking about 143, 143, which is like this: 1 0 0 0 1 1 1 1. So this is the 8 bit. So last bit has to be 1 in that case. Okay, let's do this example then. Okay. Oh, I did. Okay, these are the two numbers, and we want to multiply them. Okay. So first step multiplication with this bit, it gives this result, duplicate, and then we shift. So first step, we always introduce this 0. There is no carry forward from the addition or any such question as that. So we carry forward. So let's say this is always a fixed 0 at this point. And then we deal with this bit, which gives me, duplicate this one, but 0, 0, 0, 0. And we do a partial addition. This 1, 0, 1, 0, and my carry forward is 0 there, right? Carry out is 0. This is my carry out. Okay, so maybe we should just type in so that I can manipulate it. Let me type in. Okay. Okay. So this will become 0, 1, 0, 1 with carry out bit 0. Okay, let me just make a different number. Okay, and now we have the other one as 1. Let me color code it. Okay. Now we shift. So along this process of shifting, we are shifting this guy and we are shifting the carry. Okay, now we do next one, which will give me the same number. Okay, now we need to do an addition. So it will give me 1, 0, carry forward 1, which will be 1, carry forward, okay, this is 1. Let me see, 0 plus 1, 1, 1, 0, 0, 1, 1, yeah. And my carry out would be 0 in this case. And we have these two. Right. Okay, now we shift. We shift, bring the carry in, carry out in, show the picture, and then we do this one, which becomes like this multiplication, and then now here we are, what we have, let's see. Okay, 0 plus 1, 1, And then 1 plus 1, 0, carry forward 1, 1 plus 1, 0, carry forward 1, 1 plus 1, 0, carry forward 1. So here in this case, my carry forward amount would become 1. And we have 1, 1, 1. So from hardware perspective, now we need to shift. We basically shift this guy, 1 position, 1 position, 1 more position, 1 more position, and shift in this one. Okay, and that's how we construct the 8-bit. So this means, like, let's say with some other data, if you have a carry forward of 1, it has to be participating in the next partial addition. Okay, so these zeros are not constant 0 insertion except for the very first step. This one is constant 0. Other than that, it is the carry forward from this partial summation. That carry bit goes into the shift process. Question? Nope. Okay, so how is the project coming up? Everyone done with the addition, logical addition, subtraction? No? Anyone wants to update us? I see there is a yes one. Any challenges you are facing onto that, or haven't started yet? Maybe it's many of you haven't started yet. I don't know. Please start. If you have not started, please start, because that's what, like, at the end of the semester, I get like this feedback. This is too complex for the students who started late. The setup student who started early, they don't have any complaint. Like, they can just smoothly sail through this project. If you just keep it for the last minute, you are going to run into this problem that you'll feel it is too complex. Okay, then I don't have any other thing tonight to discuss with you guys, unless you have more question with me, or otherwise we can stop here.
Thank you, Professor.
Thank you, Professor.
Good night,
Thank you.
everybody. See you on Wednesday.
Thank
See you.
you.